see this is this strange helix that was, I sort of mentioned in the structure, and here is rhodopsin. You can see they still have the same number of helices, and you can see they still have these, some of the same features, like loops, extracellular loops up here. But here you can see this is that carazolol thing as bound to it. This is what happens when the ligand binds to it. It just sort of sticks there. It's a static picture, remember. Sorry, maybe I didn't make that 100% clear, but when you get a structure, it's just really a static picture. It's one picture. But in reality, of course, it's flopping all over the place. So here you can see this is that retinol and the rhodopsin, and it's really deep in there. And you can see there's, I don't know, it's kind of hard to see in the 3D picture, but there's a lot more stuff sort of occluding the binding site. It's covering it. It's kind of protecting it from water interfering with this down here. Here it's a little more free. It's really a more flexible or more open binding site. So also, just the thing about the helix too, it's a really rigid structure. There's more rigidity up here. Okay. There's also, you can look at it a little more detail. It's kind of overlaid over top here. Kind of forget which one is which. But anyway, there's the retinol and there's that carazolol. And these are the interacting residues. These are like the things that are nearby, these ligands that bind to it, and that are proposed, we think, they might be the reason why you get 100% effectiveness versus 0%. There must be some way that these helices move that either close it or shift it so the G proteins either like it or don't. So I was going to say, well, I think I already mentioned that retinol is an inverse agonist. It expresses 0% active. But the findings of this paper suggest that this tryptophan 265 has acts as a toggle switch for turning on this receptor. And there's really some fancy explanations of that and some chemistry going on with these other groups nearby. But that's sort of what they learned, is that there's some subtle differences between rhodopsin and the adrenergic receptor that make this thing, that make this structure change. So what is this one? I think this is kind of the point I was trying to get across. There's the carazolol, and it interacts with these particular big purple aromatic rings. Okay, let's move on. And this is just another plot that was near the end of the paper. This is kind of cool. It's like they overlaid both the structures of the rhodopsin and the adrenergic receptor as best as they could over top. And they found that the things that differed, this is like a rainbow scale of how different they are in that particular spot. So blue means something that's very similar between the two proteins, but red means something that's very different. And that gives us a picture of what's, just an overview of what's different between them. Of course, the extracellular loop is kind of outside of the scale, of course. It's very different. But there's also areas like helix 1, which is very different between the two. I don't know. Maybe the results are a little lackluster in my explanation. But this was a big deal at the time because it's never been done. And it really will help our understanding of how to design drugs. But, so here is just sort of our summary. So we have an inverse agonist state of this beta-2 adrenergic receptor. Gives us a high resolution look at it, and what's different between it is that it binds with these hormones like dopamine. They're diffusible hormones too. I guess, whatever, it's different than retinol. And you can look at what the structural reason is behind the different binding affinities and the different conformational changes that can happen in these structures, even though I failed at explaining it that detailed. So, yeah. That's pretty much the gist of it. So when I said it's updated for 2011, this whole slide series, it's because, like 2 weeks ago, they published 3 papers in Nature about sort of the same groups who've been really in this game for a long time. Actually, the first author of this paper published another paper in Nature 469, like it's a triple threat. They published on the agonist and partial agonist action of the beta-1 adrenergic receptor. They got a nanobody stabilized active state of the beta-2 adrenergic receptor, so this is the active state, but they stabilized it in some particular way. And so the things they did, they were like really intense. They engineered their own ligand, and they engineered their own G protein, and they threw it all in this nano complex, and then they got a crystal structure, and it's big news too. So this is a big advance in the GPCR field, only just happening right before our eyes. Oh yeah, this is just some other modifications that were made in the same paper that were tried. Not a big deal. Oh yeah, so get the active state. You can understand more about the dynamics if you use something like NMR. There's also this weird concept where maybe the receptors are working together, like two are attached to each other in the membrane as opposed to working independently. Some dimerization. And yeah, there you go. That's the gist of it. I'd love to answer any questions you might have. Sure.
Can you talk a little bit more about how protein crystallization is done? Like, can any protein be made into a crystal structure, or do you have to get lucky, or what's?
Yeah, I think it's really this whole crystallization business is quite an art, and it requires lots of like determination and like slight modifications of your protein, and you might get lucky. So when they figure out a structure, especially like a complicated membrane protein like this, it's a big deal. You can publish a paper just saying, I got the structure, check it out.
And is like crystallization the only method they have for studying the structure of these proteins?
No, you can use like NMR, solid state NMR, and like some other experimental techniques, but X-ray is like probably one of the more popular ones. I don't know, some structures maybe are easier to get with NMR. I don't have a huge grasp of that.
It's size.
Size?
Yeah, size is the issue. You can only do tiny proteins with NMR, and you can do any size with crystallography.
Ah. Yeah. It's also to do with length scales too. Like I think you can probe a lot more detail with certain wavelengths of the X-rays. So that's a different aspect as far as the light techniques go. All right.
How are we doing on computer-generated models of the ligand binding sites of these G proteins?
Ligand binding sites, well, that's that's really highly modeled by these drug design researchers, like even at Waterloo, and they're pretty good at that. They do like this sort of docking procedure, and they have like a computer program which like fits it in and finds the amount of energy required to fit it in the most stable spot. But what was really cool about these 2011 papers, I didn't actually cite them, I guess they're here, is that they did do a full computer simulation of atoms, like an atomistic simulation, where they like placed each individual hydrogen, and they kind of just pressed play, and they saw how it moved, and saw if it was stable, and they can test things. But that's really cutting edge. This is 2011. They use a special computer. They didn't even use a computer, like we have huge computer clusters at Waterloo. They made one specifically designed to do molecules. Like they made hardware, like they engineered boards to simulate proteins.
Do you know how long to run that simulation?
I don't know. I'd be interested to know because I do simulations. My research is like in the molecular simulation, like computer world, and simulate for weeks, like doing like some wussy ass thing. Yeah. The papers are kind of complex. Like I don't have a big background in this, but I mean, I'm pretty sure even after this, you could probably read the abstract of these Nature papers and kind of figure out what they did. What's up?
What's the push for doing G proteins in membranes that don't have to be modified, so that you can get sort of more of a natural state protein that you can analyze and look at?
Yeah, I don't have a good sense of. Well, what do you mean? Like, do you want to get the structure of what a GPCR would be with a protein, a G protein?
Yeah, well, it seems to me that some people might think that having an altered protein might, say for like drug development or things like that, might, kind of throw a wrench in there.
Yeah.
And so I wonder what the push is from people in that field to find proteins that are unmodified or trying.
Well, they want that, of course, but you have to make some sacrifices to get these structures. I don't know if there'll be the technology to do that, but the future, maybe. It's 8 o'clock, and maybe the snowstorm's already started, so maybe we should wrap up.
Thank you, Chris.